Hello, everybody. This is the video on correlation and simple regression. This is the first thing in the new unit. All I'll say is I believe that this new unit is significantly easier than the number of calculations in ANOVA and is probably easier in terms of calculation. We'll get into the other stuff in a bit, but just let's concentrate on this topic of correlation and simple regression. And what I'll say is we're actually going to be doing a few types of calculations for problems here, but the calculations are very similar, and we're going to be using the same data. It's just looking at from a different perspective. So you'll see what I mean as we go on, but we're going to take a couple different perspectives on the same data. And basically, correlation and simple regression are the same thing. Correlation just talks about a relationship between two variables in terms of a line, and simple regression is that line. And so the correlation is usually the number, which will indicate the type of correlation it is, positive or negative, and how strong it is. And we'll talk about that as we get through the lecture. Whereas simple regression expresses it as a linear equation, which you probably studied back in middle school, junior high school, at least. So let's move on with this lecture. There's a number of slides, but actually it's relatively easy. And so again, with the correlation, we're measuring just the relationship between two variables. And the correlation indicates several things. First, it indicates the direction, whether something's positive or negative. So if something has, if the correlation, if it doesn't have a sign, usually it means it's positive. And so positive correlation is as one thing goes up, the other thing goes up. So let's say I measure a bunch of people's height and weight. I'm guessing there's going to be a fairly good positive correlation between people's height and weight. It might not be a perfect correlation, but I'm guessing there's a positive correlation. And then negative, which is indicated by a negative sign in front of the number, means as one thing goes up, the other thing goes down. So I'm guessing that the number of hard liquor drinks that you drink the night that you're studying for an exam is probably negatively correlated with the grade you get on the exam. So if you're drinking hard alcohol and you correlate the number of those drinks with the grade on the exam the next morning, let's say, I'm guessing there's probably going to be a negative correlation. And the correlation is simply, it's a line. What happens is in the data, it fits, the equation fits the best line of the plot of the data. So we'll talk about that a little bit later. I want to just say it's a linear thing. We'll look at some actual graphs in a bit. It'll be easier to talk about then. And then the strength. And so 0 to 1, and this is a absolute value, so we're ignoring whether it's positive or negative. Positive or negative does not mean anything about the strength. Positive or negative just tells us what direction the relationship is. The 0 to 1, the magnitude tells us how strong it is. 1 is perfect. So 1 is, as you change one unit in one variable, it goes up 1 unit in the other variable if it's positive, and it goes down 1 unit if it's negative. If it's 0, there's no relationship, there's no correlation. They just co-occur randomly. There's no relationship between the two. So again, this is the absolute value, with 0 being no relationship and 1 being perfect, where a change, 1 unit change in one variable is equal to 1 unit change in the other variable. And the possible range then is -1 to +1. So in the middle of that is 0. 0 means no correlation whatsoever, no relationship between the two variables. And then +1 is a perfect positive correlation. And -1 is a perfect negative correlation. So again, the positive and negative just tells us about the direction of the relationship. 0 to 1 tells us how strong the relationship is, with 1 being the strongest. And here's the lines, and that's sort of saying the line of best fit. So if we have this type of data, the correlation tries to fit a line that basically minimizes the distance between these blue dots and the line. And we'll talk a little bit about that later when we talk about regression. So that's what we mean by linear, is our formula will plot a line that will describe the relationship between two variables as a correlation, as a linear relationship. So here, it's actually supposed to be a zero correlation here, probably, between shoe size and IQ. If you look at it, it's kind of random. The dots are all over the place. There's probably not a correlation, and we would hope there wouldn't be a correlation between shoe size and IQ. Look at IQ scores and college GPA. What sort of correlation do you think is here? So to me, it looks like there's probably a weak or moderate positive relationship. So if we look here, it's not perfect, certainly, but it looks like as IQ scores go up, as we go higher here, the GPA goes higher. So if the direction of the data are going this way, that's a positive correlation, because low IQ score, low GPA, high IQ score, high GPA. But again, this is not perfect. It's probably a moderate or weak correlation, positive correlation. And then here, look at monthly salary and annual salary. And so ask yourself what sort of correlation this is. Hopefully you said it's a perfect positive correlation. It should be, actually, because these two are just the same thing, just looked at differently over a year versus a month. So it looks perfect because it's all lined up. We can actually draw a line here. Here we will draw a line. The mathematics of the correlation draws a line, but you can see once we draw the line, there's going to be a lot of dots that are off the line. Here we can draw a line and all the dots are on the line, so it's a perfect correlation. And what is it? It's a perfect positive correlation. As annual salary goes up, monthly salary goes up. And so this is a scatter plot. And so in a scatter plot, you are just plotting each person's scores. So family income is on the horizontal, and then grade is on the vertical. And so for each person, you plot here for person 1, 31 and 71. Next person, 38, 86. 38, 86, probably here. And so each person's data gets plotted that way. So that's what a scatter plot is. Each of these dots is a person, and their score on this variable related to their score on this variable. You won't have to do this, and you probably know already what this is. I'm just sort of going over it real quickly. And again, as I said, what you do in correlation is that you are finding what's called the line of best fit. What that means is that you find a line that you minimize the distances between the line and these dots overall. So mathematically, what the formula is doing is saying this is the best line to minimize all of these distances from the real dots from the line. And so here's another example, temperature and amount of beer sold. And so here there's a positive, pretty strong correlation. And I grew up in Wisconsin. I don't know if this is actually true. It's cold in Wisconsin, but summers are hot. I don't think beer sales varied much, but these are just fake data, so let's not get into it. And then let's look at coffee sales and temperature. And so here, what type of correlation is there? Hopefully you said it's a negative correlation, because as temperature goes up, coffee sales goes down. I guess here we're applying hot coffee, not chilled coffee. And it looks pretty strong. So positive, as temperature goes up, beer sales goes up. As temperature goes up, coffee sales go down. It's a negative correlation. Okay, let's look at these different types of correlation. So let's look at A first. So what is A? How would you describe that correlation? Hopefully you said it's a perfect negative. Why do I say it's perfect, for one, is we have a line here, and all the dots are on the line. When all the dots are on the line, it's a perfect correlation. So this is also negative correlation. As we get higher on X, we get lower on Y. So there's a perfect negative correlation in Y. B, what sort of correlation is there? Hopefully you said 0. It looks like there's no correlation, or I guess we could call it the chocolate chip cookie effect. Looks like a chocolate chip cookie to me. But it looks like there's kind of random stuff there. It doesn't look like there's any direction to the dots in terms of the relationship between X and Y. How about C? How would you describe that? Hopefully you said it's a fairly strong. Why do I say it's strong? Because the dots are closer together. So the dots are closer together. It's not perfect. When we put a line here, the dots will be off the line, but it's pretty close together. So it's a fairly strong positive correlation. As scores on X go up, the scores on Y is going up in general. How about D? Right here. I'm hoping you said that it is a weak negative correlation. For one, why is it negative? Because it looks like in general the data is going in this direction, so that as we get higher on X, we're lower on Y. And I'm saying it's weak because if we drew a line, there's a lot more distance between the dots and the line, and you can just kind of see it from the circle. This circle is tighter, and this circle is looser. So if the circle around the data are looser, then it means it's a weaker correlation. So again, that on D looks like a weak negative correlation. So basically, when we're doing a hypothesis test, and you don't need to state the hypotheses anymore, you know how to do that already. It's basically, if we have a non-directional hypothesis, two-tailed, then we just say the HO is the correlation, P is the value of the correlation for the population. The correlation is 0, and the alternative is not 0. However, if we have a directional one where we think we have a positive correlation, like here, so our HA would be the correlation is greater than 0, it's a positive correlation, then our HO should be the correlation is equal to 0 or negative. And vice versa. If our alternative hypothesis is that there's a negative correlation, our HO is the correlation is equal to 0 or is greater than 0. Because if it's a positive correlation, then we for sure are wrong in our HA if we said it's a negative correlation. So again, you don't need to state these. This is just what's happening in our hypothesis test. So we already know that we're in an inferential statistics, and correlation is an inferential statistic. We're using sample data to test and make inferences about the population. And then our degrees of freedom is pretty easy in this case. We only have one, so it's not like the ANOVAs where we have 3 to 5 degrees of freedom. We have 1 degree of freedom in a correlation. And simply the degrees of freedom is n minus 2. So you can think about n being the number of people or number of things you're looking at. And it's minus 2. Why is it minus 2? Because we have 2 variables. So we have one variable. Let's say it's the beer sales. That's what I'm remembering. I don't drink, by the way, but it's stuck in my brain for some reason. Maybe from Wisconsin. I think that's in my blood, even though I don't drink it anymore. I'm a boy from Wisconsin where beer's everywhere. So let's think about beer sales. That's one variable, and then temperature was the other one. So we have 2 variables. So each variable gets one of these minuses. So we have beer and we have temperature. That's 2. So negative 2 because we have 2 variables. And so officially, actually, that n, that small n, is the number of pairs. Remember that for each correlation, we have pairs of scores. So we have a score for temperature and beer sales. So it's a pair of scores. We plot that. We look at another day. We look at the temperature. We look at beer sales. We plot that dot. So Each pair of scores, so each day we look at, day is what we're sampling here. So number of days we have, which is the number of pairs of scores we have in temperature and beer sales, minus 2 is the degrees of freedom. Let's start out with the most common correlation that most people think about, mainly because it's sort of what we kind of think of anyway. When people say there's a relationship or correlation between things, we often think about this. So the Pearson correlation is, we're looking at the relationship of two variables, and each of the variables is at least approximating interval level measurement. So each of the variables has numbers that we can actually use as numbers. We can add, subtract them, etc., do mathematical operations. So it's, again, the relationship between two variables that are measured at least approximately on an interval scale. So interval and ratio. We'll talk about ordinal in a bit. We're actually going to do one ordinal analysis in this lecture because I think we should do one ordinal thing just to show you how ordinal data is dealt with in general. And so we're sticking with this one first, Pearson correlation, two interval level variables, interval/ratio. And we're going to talk about that. The perfect relationship is that when x changes 1, there's a corresponding change in y. And so basically, conceptually, what we're looking at here is this ratio. So R is the abbreviation for correlation. So R, in terms of a Pearson correlation, is the covariability of x and y over the variability of x and y separately. So what does this mean? Let's look at the bottom first. So remember when we talked about ANOVAs, we talked about the bottom, especially in a one-way ANOVA, if we're looking within groups, variability. So we look at the red group and we say, well, our best prediction of what attraction scores people will have in the red group should be the red mean. But we know that people differ from the red mean because there's probably some individual differences or other things going on. So not everybody's on the red mean. So there's variability within that red group. So I was talking about that conceptually with the ANOVAs. That's a measure or an assessment of just how people vary in general. So this is similar here. We have two variables in this case. We're not just looking at the dV of attraction. We have two variables going on. So we're actually going to look at the variable of those two things on their own. And it's kind of it's again a measure of just kind of how do these two things vary on their own in general. How much do beer sales vary day by day? How much does the temperature vary day by day? Just in general, just naturally. And then the top of that is how much do they co-vary together? And co-variability is if beer sales goes up, does temperature go up? Here I'm not talking about causation, I'm just talking about the mathematical relationship. So co-variability is if one goes up, does the other one go up? That's a positive correlation. It could also be the opposite way. So if beer sales goes up and temperatures go down in general, that's also a correlation. It's co-variability. It's just a negative co-variability. Because as one goes up, the other variable goes down systematically. So basically what we're asking here is this ratio is, do these two variables dance together, whether it's a positive dance and they both go up or they both go down, or whether it's a negative dance, one goes up, the other goes down, one goes down, the other one goes up. So are those two variables dancing together in a pattern? So here the ratio we're just asking is, does that dance? Is there a pattern of them going together, dancing together, whether it's in the same direction or opposite directions, if it's negative? Is that dance, is that pattern stronger than just how those two things individually vary? So conceptually in this case, if beer sales and temperature vary together, and that variability that they are strong, they have a strong pattern that they're varying together, if that is greater than just how beer sales alone and temperature alone vary, then we have evidence that there's a relationship. So the dance, the going hand to hand, changing together between beer sales and temperature, if that is stronger than just how they walk apart separately and vary separately, then we have evidence that there's a relationship. So it's a similar logic. It's that variability. So in ANOVA, it was variability between groups over variability within groups. Here, it's variability in terms of things going together, two variables going together in a pattern. And is that stronger than just how those two variables separately and individually differ day to day? So that's the rationale of a correlation. It's very similar to the rationale of an ANOVA. It's this ratio. And here's a simple little illustration of covariability. So this is actually from another textbook. It's a British author. And so we have some British terms here like adverts, so advertisements. And so it's looking at the relationship between how many advertisements, let's say, are on the television and how many things people buy. This packets of some sort of thing that you're advertising. Not sure what the packets are, but it could be packets of candy, let's just say, because I like to stick on this sweet tooth thing from the chocolate chip cookie early on. So you're advertising the packets of candy, and then you're correlating it to how many packets are sold in that area that you had the advertising on TV. So is there a correlation? So what we're basically doing with the correlation is that we first have to ask, what's the average for the two variables? So this line right here is the average number of advertisements on television. And here we have people. So how many adverts the person saw? Advertising, television ads the person saw. And so here's the average. So if we just look at the number of adverts our 5 people saw, this is the average. This is the line. And then we have variability. So some people, person 1 saw less than average, just a little bit less than average. Person 2 and 3 saw considerably less than average. Person 4 saw a little bit more than average, and person number 5 is a couch potato, I guess, and they saw a ton of adverts compared to the average for the sample. Same thing for packets. So how many packets of candy did you buy? And they ask each of these 5 people. And this is the average. This green line is the average number of packets that were bought by the sample of 5 people. And again, we see that person 1, they buy less than average, quite a bit less than average. Person 2, less than average. Person 1, a little bit less than average. Person 4, they bought a little bit more than average. And person 5, they bought a lot more than average. So what a correlation is actually looking at is, we know that we're going to look at the variability in general. So the lines here are variability. So we can look at the variability for adverts. We can look at the variability for packets. That's on the bottom, remember? That's on the bottom. But on the top, we're going to ask, are those things going together for the different people? So we have people in this case. Sorry about this. I'm going backwards. So we're in that co-variability part, that top part, we're asking for every person, if they see more adverts, do they buy more packets? And conversely, do they buy less packets when they see less adverts? And we can actually see this here. So if you look at this right away and you're good with numbers, you might say, oh, there is actually a correlation. It looks like there's a positive correlation. If you don't see it, I'll show you. So person 1, they see a little bit less than average advertisements and they buy a lot less packets. So we already have a positive correlation, although it's not perfect, obviously, because it should be -3 and -3 or something like that. It'd go hand to hand. So it's not perfect, but it's going in the same direction. Person 1 They're below average on adverts, and they're below average on packets. They're going the same direction. Person 2, they see considerably less number of adverts than average for the sample. They buy less packets. Same direction. Person 3, they see less adverts, they buy less packets. Same direction. Person 4, they see a little bit more adverts, they buy a little bit more packets of candy. And then our couch potato, who sees a bunch of adverts, they buy a lot more packets of candy than average. So for every single person, this is not going to happen in real life, but just for an illustration, it's for every single person there's a dance there. That if they see less adverts than average, they buy less candy than average. If they see more adverts than average, they buy more candy than average. So it's going in the same direction, so it's a positive correlation. And there's a dance there between the two variables, between seeing adverts and buying candy. So this is definitely going to have a fairly strong co-variability. As adverts goes up, candy buying goes up. As adverts go down, candy buying goes down. There's a co-variability between the two. And it looks pretty strong, and it looks, to me, it looks probably stronger than just how much is varying here. I mean, they're not varying a whole lot on packets or adverts. There's a bit of variability, but not a whole lot. So I'm guessing the co-variability here is probably pretty strong. So we probably have a decent positive correlation here. So this is just conceptually what we're doing, is we're seeing if there's a pattern of co-variability in terms of from the average. Are you above average? These two people are above average in both. Are you below average in both? So there's a co-variability. This is what the correlation is doing conceptually. And so here is the formula. You won't understand the full formula yet because I'm not giving you the top part yet. So basically this ratio, which again is conceptually the co-variability of x and y over the variability of x separately from the variability of y separately. So SP is actually going to be the measure of co-variability. We're going to get into that in a bit. I'm going to give you formulas for that. And then what's the variability of x and y? Well, let's use the sum of squares. That's something that we've used. So the sum of squares calculator, we're going to be using this. So we're going to take the sum of squares for x. We're going to take the sum of squares for y separately. You see here, we're going to multiply them. And then we're going to take the square root. So how do we do sum of squares? This is the mathematical formula. You don't need to use this. Again, for the sum of squares, you can use the online calculator. I have a link for that later. But how about SP? So remember, SP is the top part. That is our measure of co-variability of x and y. So how do we figure that out? Here's the definitional formula. But this is not the one we're going to use because this will take longer, but it should look a little bit familiar to you. We have two variables. And for these variables, we're going to look at each variable separately. So we're first going to look at x. Let's say that x is advertising from the last one. So we're going to, for every person, we're going to compare their score from the mean of x, which is actually what we have here. So for every person, we're going to subtract their score, the dot, from the mean, the line. And we're going to have that all together. And then for each person, we're going to do the same thing for y. So we do this with each person. So each person, how far are they from the mean of adverts, and how far are they mean from the mean of packets? And we're going to multiply those two. So that's what that's telling us, is for every person, look at what their score is on the first variable, adverts. How far was it from the mean of that variable for adverts? For the same person, what was their score on buying candy? And subtract that from the mean of buying candy. So we're just, for every person, we're looking at these two combined. How they vary from the mean. This should look familiar because our sum of squares actually is that for one variable. Remember when we did the sum of squares to get the standard deviation, we had to look at everybody's score and subtract it from the mean. But in this case, we do not square it. Why don't we square it? Because we don't want to square it. We don't want to get rid of direction here. So here we want to know whether there's a positive or negative direction. So anyway, this is the formula. We'll understand this better with data. This is the definitional formula. So definitional formula is just what we had in the graph. How far is each person varying from x, the average of x, the average of y? That's the definition. Luckily, we don't have to do that. We can just do a computational formula. So this definitional formula would take a lot longer. This is easier. So this is how we're going to do it in our problems. And so we're actually going to, for every person, we're going to multiply their score on x, their score on y, and then add it for every person. And then we're going to add everybody's score on x separately, add it together, add everybody's score on y separately, add it together. We're going to multiply those two things and divide it by n. N is the number of people in this case, would be 5. There's 5 people in that little example we just had. So this is a pretty easy formula, and I'm going to take you through how to do this in a sample problem pretty soon. So if you have the textbook, we have another critical value table for R. So every statistic, we have a table that we need to look it up, what the critical value is, and see if what our computation is higher than the critical value. So table B6, if you have the textbook, is the critical values for R. If you don't, there is the link. The link looks like this. And so here, what we just basically do, remember that we're going to do a one-tailed test. We're going to stick with one-tailed test. So one-tailed test, right here, this line, we want the 0.05, that's our alpha. So we're going to stick into this column. I can't highlight the column, but this column that follows down here. And these are the degrees of freedom. So unlike the ANOVA, there's just 1 degrees of freedom here. Remember, it's n minus 2. We have 2 variables. So if we had 5 people like this example, it would be 5 minus 2, so it would be 3. So what we would do is we take the 0.05 for the one-tailed test right here, and we go to degrees of freedom 3, and a critical value would be 0.805, which is quite high, but that's what happens when you have a small sample size. Okay, so there's the table. And by the way, the sum of squares calculator is right there. They're advertising El Pollo Loco a lot, so I hope you're not hungry when you look at that. That's an unpaid advertisement. I do not get paid from El Pollo Loco, but if you know anybody there, contact me and maybe we'll set up a relationship. So that's the critical values table. And I just highlighted that's the sum of squares calculator. So you can just use that link for the sum of squares. Each number is just a separate line. So it's the same thing we were using for the ANOVA calculations. Okay, before we get into examples, why do we use correlation? So prediction. So remember, we have a line. So if we say that, that's really far. But okay, here's we have this data, and we have this line. Sorry about this. We have this line. What happens is I have the least expensive, newer type of laptops, which means I have a not that great laptop. And so every time I lean on it, it presses something and it thinks I'm pressing a button. So that's why I go off the slide sometimes. So we can make predictions. So we have a line here. So based on these data, we can make a prediction about a new day. So we can say, oh, tomorrow is going to be 85 degrees. And so if we know it's going to be 85, I picked something that was, this must have been done up north. So let's go a little bit lower. Let's say I think tomorrow we have a prediction it's going to be 65 degrees. So using this line, I could say, well, if it's 65, then beer sales should be around 45. So that's how I can do a prediction with that line. If I know the value of one number, I can predict the value of the other number. Of course, there's going to be some errors in that prediction, but it's not going to be that bad over time. It should be relatively good if it's a strong correlation. If you have a weak correlation, of course, there's going to be bigger errors. And if you have no correlation, you should not be doing predictions. So the prediction is really when there is a significant relationship. You can also use correlations for validity. Validity is when you have a measure and you want to provide evidence that the measure is assessing, giving a number to the thing that you say it does. Validity is that you say you're measuring something and you have some evidence that it is actually doing it from outside the measurement itself. So let's say that, I guess I'm on a narcissism thing today. So let's say that I made a self-report questionnaire on narcissism. One way I could validate that is I could give it to a bunch of people, and then I could bring those same people in and individually, and I could have them do a task in the lab, and I'll have a recording of that task, and then I'll have, let's say, 3 experts on narcissism rate that person's behavior in terms of how narcissistic they are. So some validity evidence would be if there's a positive correlation in narcissism scores between my questionnaire and what those experts said about the person. So if there's, again, a significant positive correlation between those two, the questionnaire versus an expert's assessment of how narcissistic somebody is, that correlation can provide evidence for validity, that I'm actually, indeed, my questionnaire is actually measuring narcissism, because the observers generally agreed on how narcissistic those people were as individuals in comparison to my questionnaire. Also for reliability, reliability just means that the thing that you're measuring, is it consistent? There's different types of reliability. This is not a methods class, so I'm not going to get into all the types of reliability. Let's deal with the easiest one. Let's say that I, again, have this questionnaire on narcissism, and I think narcissism is a personality variable that therefore should be consistent over time. So if my measure is reliable, if I give the narcissism measure to you now, today, I get your score for it, then I wait, let's say, 2 months, and I give you the same questionnaire, and hopefully you forgot the questions and how you answered them. You take it again in 2 months, then I could correlate your score from today to your score 2 months from now. And again, if there's a significant positive correlation between those two things over time, then I have some evidence that my measure of narcissism is consistent over time, which is called test-retest reliability. Then I have some evidence of reliability of my questionnaire. Again, that's through a correlation. And here's this theory verification. That's just a fancy way of saying it can be used as an inferential statistic. So you have an idea that narcissism is related to being a jerk to other people, and I can go out and collect data on these two variables. I can measure narcissism, I can measure how much you're a jerk to other people, and then I could, one way of analysis, I could correlate those two things, providing that they're interval or ratio level measurement. I could correlate those two things, and that would be an inferential statistic testing out my hypothesis that those two things are positively correlated based on my theory of narcissism. That's what that's saying. Okay, there's quite a bit of conceptual stuff here before we get to the problems. So correlations only measure the range that you actually have in your sample. So this can be seen actually right here. I'm going to show you this first because I think all those words don't make any meaning unless you kind of know what's going on first. So let's say that we measure just people who are out here. So whatever this is, let's say this is narcissism, so we're talking about this, narcissisms and being a jerk. Let's say that I make a special way of recruiting people. Maybe I'm recruiting people who are executives or people from certain fraternities in Stanford University. I shouldn't say that, I'll get sued. But I had a roommate in grad school at Santa Cruz, and he got his bachelor's in Stanford, and he was a frat boy, and he was probably the biggest jerk I had ever seen. He seemed very fun when you first met him, but living with him and seeing how he treated other people, he was a jerk for sure. So let's say I recruit people, and somehow my sample ends up being people who are high in narcissism and tend to be highly jerkish in their behavior anyways. And, so it's relatively high in both. And I kind of look at this little limited range, and maybe there's no correlation here. It doesn't really stand out. It looks like that chocolate chip cookie. It just kind of looks a little hard to predict. But if I did a broader sampling of people and got more variability in narcissism, more variability about how jerkish they are, now you can see that when we measure a broader range of people, it's starting to look like a positive correlation. Here, if we just look at the chocolate chip cookie, it looks like nothing. That's because we're looking at a very limited range of people who are high on both in this case. But when we measure a broader range of people, then the picture becomes clear that there is a positive and pretty strong, at least moderate, it's probably actually strong, it's pretty strong positive correlation. So all this stuff about restricted range just means that we have to be very careful when we have a sample where there's not a lot of variability in the variables that we're looking at. We could actually come up with some false conclusions for one. And for two, when we have a restricted range like this, we better say that in our findings. We could say there's no correlation between narcissism and being a jerk. However, our sample was particularly high on both. Therefore, we have a restricted range of scores, and therefore we cannot make conclusions about a broader population of people. So when we make our generalizations of the data, we really should be very careful not to go beyond that range that we actually collected, because we have no idea what's going on beyond that range. What I would say is what you really should do is then broaden your sample. If your initial sample looks like this and you have a restricted range, you should probably slap yourself in the face and say, I need to go recruit other people who are in this area so I can see really what's going on with people. So correlations and outliers, I need to talk about a couple things here that your textbook talks about. One thing is, and I believe this is a quote from your textbook. If it's not from your textbook, it's from another statistics book. An outlier is an extremely deviant individual in the sample. I think I talked to you about this before in class. This is one of the things I hate about statistics. I think sometimes people who are in statistics, they dehumanize people, and they see people who are deviant, quote unquote, as bothersome because they don't fit their models well. Because you're trying to get that little line. I'm gonna have to go back quite a bit, but it's an important point. So people. It's not bad here. People are kind of not too far from the line, but a deviant person, quote unquote, would be over here or would be over here. And statisticians don't like people over here or over here because it messes up their line. It messes up their model because they're caring about the numbers. So one of the things I want to talk about here is I totally disagree with this. Sometimes what statisticians sometimes do is sometimes they drop outliers. They call it overly influential outliers, which means that this is the second point, actually. The more conceptual point is if there's an outlier here, let's say there's an outlier over here, it's going to draw the line this direction. So just like with a mean or standard deviation, any sort of averaging of stuff is going to pull the line that direction. And it's going to pull the line in that direction more than this one pulls it that direction, or this one, because it's further out. It's quite different. So it's gonna have an influence of pulling that line over there. Same thing if we have something over here. If we have an outlier in this direction, it's going to pull the line down this direction. And so outliers, because they're extreme, they can actually pull a line a little bit further than the other scores. So because of that, sometimes statisticians say that you should drop these overly influential outliers because they mess up their models. I think that is a horrendous state of things. I personally think if you cannot fit everybody's score into your statistical model, then your statistical model needs to be modified. It's not that you should drop people from your data. I think that is a horrible practice that has happened. In my opinion, the only reason to drop anybody from your data is if you think they were lying or acting weird, or in essence, their data wasn't valid. They didn't understand the questions you were asking. They were lying on purpose. They were acting weird because maybe they were drunk when they came into the lab, or some sort of weird thing happened that day. Then I can see having a good argument for dropping their data, because it was under strange conditions and the data probably are not valid in that case. But for dropping data that certainly you have no evidence that it's invalid, just because they don't fit your model, I think is a horrible thing to do. So let me get back to that slide. That's a long way to go. Oops, here we go. And so this is where the language comes in that first sentence, which I totally disagree with. And so basically an outlier is just basically, and I talked about this already again, so an outlier is somebody who doesn't fit, is clearly different from the other points of data. And because they are farther away, they have tend to have a larger influence on pulling the line towards them. And here's just an example. So here's our chocolate chip cookie, but it's somebody who is very stingy on the chocolate chips. So we have here a correlation that's basically 0. It says negative 0.08, but that's 0 basically. We would not be able to say that's any different from 0. So there's no correlation there. It's the old chocolate chip cookie phenomenon. And then let's say if the data, we had one other person, but they were extreme, they were outlier. And if you calculate these things, then all of a sudden the correlation becomes a significant positive correlation of 0.85, which is very strong. So the argument here is we have to watch out for things like this. But the truth is, if you have a larger sample of data, nobody's going to change a negative one. No one person is going to change a 0 correlation, no correlation, to a significant correlation all by themselves. If you have a decent sample size of 20, 30, something like that. So I think this is kind of an exaggerated viewpoint that's being presented here. And again, I believe as long as you don't have evidence that the data is not valid, you should not be dropping people just because you can't fit them in your model. Then your model needs to be changed again. You should not be dropping people from your study. And this shows sort of the same thing. So here the outlier is pulling the line away from the other dots. But again, here we have a relatively small sample of, it's bigger, but it's maybe 15 or so. And then once you remove the outlier, then you have this perfect, nice little line. So again, a lot of statistics books talk about people as if they are bothersome, if they don't fit the model. So this is a great thing because we can fit this nice little line here and screw this other person. Let's just drop them. Well, maybe you should be using, if you don't like what your correlation looks like here, if it doesn't describe your data, then maybe you need to use another more sophisticated analytical technique to make sense mathematically of what's going on here, rather than just dropping somebody for no real reason except to improve your statistics. So again, we talked about the strength of the correlation going from 0 to 1. When we talked about the magnitude or the strength of the correlation, we ignore the positive and negative. Positive and negative just tells us the direction. Again, positive, one thing goes up, the other one goes up too. Negative, one thing goes up, the other one goes down. And what this is saying is that people sometimes mistake that as some sort of percentage or degree. You can actually, if you know statistics well, you can interpret it, but it's not a percentage. So typically what you do, so with all our inferential statistics, we've been having our statistic and then we've been having our effect size. So this is actually, the effect size is the squared correlation. Remember R squared, our little friend from the t-test? Remember R squared equaled to the t squared over t squared plus degrees of freedom, that little formula? Well, that's R squared is coming back right here. So if we have R, which is our correlation, so we calculate the R from that formula that we had way back when. If we take that number and we square that number, we square R, we get R squared, which is the exact same thing as our interpretation for the t-test. So R squared is always going to be the percent of variance in one variable that is accounted for by the other variable. So here they call it shared variability because we have the correlation between two things, because they don't want to make an inference about causation like a DV and IV, that type of stuff. So it's just the shared variance. So how much, again, it's the same as what we had before. So in t-test we said what percentage of the variance in the DV was directly linked to the IV. It's the same thing for this. So let's take the beer sales and the temperature, and there's no IV there. We're not manipulating either. And so, and I guess we shouldn't buy beer that day, because if we're buying beer that day, we're manipulating the variable. And unless you buy a lot of beer, I guess it'll still be the same anyway. So we have beer sales and we have temperature. So we have two PVs. We're not manipulating them. But what we can do with this is, probably we're curious about the beer sales. That's why the beer sales, I think, was on the vertical axis in the graph. So we can ask what percent of variance in beer sales is directly linked to changes in temperature. R squared would tell us. So if we found a correlation between temperature and beer sales, we squared that correlation, R squared, that would tell us what percent of the beer sales is directly linked to changes in temperature. Again, this R squared, it wouldn't be statistics if they didn't give you 5 different terms for the same stupid thing. So this R squared sometimes is called coefficient of determination. What does that mean? It's the percent of variance in beer sales that's directly linked to the changes in temperature. That's called the coefficient of determination. So we just talked about that. There's another issue with correlations, and we'll kind of bring it out in this graph. So let's look at the correlation between these two variables. So one variable on the horizontal is number of churches, and the other variable is number of serious crimes. So we could go maybe neighborhood by neighborhood, or we could go city by city and measure the number of churches and then see how many serious crimes are committed in that same area. So here we have a positive correlation. So this means that churches leads to serious crime, correct? I am guessing that you are saying no. So oftentimes they talk about correlation does not equal causation. Statistically, we sort of say that. I won't get into the details of this. Causation has more to do with your method than your statistics, but your method mainly being whether you have a manipulated IV or not. But let's just stick with the correlation here. So here, I don't think you want to say that churches cause serious crimes. So what could be going on here? Why is there such a, and there's a strong relationship. What's going on here? Why is there a statistical correlation between these two variables? I'm hoping you're saying something like, if it's like cities, maybe it's just because if you have a bigger city, you're going to have more churches. You have a bigger city, you have more people, you're going to have more crime. If you have a smaller city, you're going to have less churches. Smaller city, there's less people, there's going to be less crimes. And this is just number of crimes, not percentage of population. So there's what we call a third variable here. The third variable is population of the city. Population of the city is determining the number of churches. Population of the city is determining the number of serious crimes that are committed. So this is what we call a third variable problem. So if you do a statistical correlation, we have to be careful about making any inferences about X causing Y, because there could be a third variable that you did not measure, that you did not include in your statistics, that's actually driving this relationship. So again, that's called a third variable problem. That third variable of city size is driving both of the variables in a certain direction. Big city, more churches. Big city, more crimes. Little city, fewer churches. Little city, fewer crimes. So that third variable is driving both of these variables together, and it's looking like they're co-occurring, but it's really because that third variable is influencing both. So here, they've actually split this up into large cities, medium cities, and small cities. So large cities, here's the correlation. Doesn't look like it's really much of a correlation. Maybe a slight positive one. Medium cities. Medium cities. Looks like a little square here. Sorry about that. I'm leading on the laptop. That's why it's doing that with my slides. So medium cities are just right here. It looks like a little box. It looks like a zero correlation. And then small cities, looks like there's no correlation, or maybe even a negative correlation. So if you split up the data and look at large cities versus medium cities versus small cities, it doesn't look like this. It looks like this, and it looks like the correlation between churches and number of churches is either negative overall or might be slightly different for the different types of cities. Maybe it's slightly positive for large, slightly negative for small, and zero for medium. So when you have a thing like that, just in any research actually, it's much better to actually have more variables measured if you can, so that you can account for these things that are more complex. So I think sometimes this gets wrote a lot in stats books because they want to proclaim that experiments are the best things, and that non-experimental research, which could use correlations as a statistical analyses, are horrible because of all these problems. I think a lot of that is just bullshit. The big thing is, are you doing research methodology and design where you are looking at something that gives you a complex and accurate picture about things? It's not necessarily about data. So the data are only as good as your research design. So I think this is a bit of what we call a straw man. I think a lot of this is kind of being set up as a way to bash non-experimental research in social sciences, and I think that's kind of a load of crap in many ways. And here we can just see a simple example that I don't think any social scientist would do a study like this and make the stupid conclusion that books like to talk about, that these things are correlated. The reality is that, maybe somebody would do a study like this where they do measure the size of the cities and see that the pattern differs according to that. It's a more complex explanation. So again, I think this is a little bit of a straw man, but you need to know this third variable thing, because if you're going into social science and you're going to transfer, for sure you're going to encounter this, or even if you don't transfer yet, for sure in your research methods class, you're going to encounter this sentiment also in social sciences. Okay, this next topic, and we haven't done any calculations yet, so this next topic, I'll say don't look at the formula. Avoid the formula. The formula is there just if for some weird reason you want to use it in your future. But we want to talk about this conceptually. We are not going to calculate this. So partial correlation is sort of what we were just talking about. So we have two variables here. We have churches, number of churches, and number of serious crimes. So we have two variables. It's just a simple, what we call bivariate correlation. This variable, two variables, bivariate, bicycle, two wheels, bivariate, two variables. So it's just a simple relationship. But then this next slide, we're actually doing a partial correlation. So what's the partial correlation? Well, we're looking at the overlap between those two things in a third variable. So if we look at city size, then it's probably very unlikely that there is a simple correlation between churches and crimes. What we say, it would depend on the cities, because it looks like large cities might be slightly positive, small cities slightly negative, and medium zero. So that's kind of what a partial correlation does. It sort of says, well, let's look at two variables together. Let's put a third variable in there and see if that relationship between these two variables holds still. In this case, it doesn't hold. The relationship looks different according to the size of the city, that third variable. So partial correlation is this very same thing, conceptually. And so what a partial correlation does is we want to look at the overlap between the two variables. So this could be the number of churches. I'm not saying this is specifically because it would actually be a zero, but let's just say theoretically this is the number of churches. This is the number of serious crimes. And the correlation is actually this whole thing here. I kind of feel like I want to snip this. And I'll make it bigger. It's good. Let's say that 1 is churches. So let's say 1 is number of churches. And 2 is the number of violent crimes. The correlation is literally this overlap. And it's hard to see here, so I'm going to make it. It's this line over here. It's the full little. Again, I'm not trying to be right on a line, because if I did it right on a line, you won't see it. So it's this area, this little, it looks like a football. No, it looks like a hairy football. So it's that whole overlap there. Let's just say theoretically, let's just say that we looked at the population. So it's the third variable here. So we'll see that the population comes in here, overlaps with the number of violent crimes. It overlaps with the number of churches. So there's this part here, that population overlaps with both violent crime and with the number of churches. And here it looks like there's probably a positive correlation. So what we were saying here is that there might be a strong correlation. Let's just say this initial correlation is high, and it looks like it's maybe, let's say, 0.40 or something like that. So R is 0.40. But then once we look at the population, this third variable, and we're looking at a partial correlation, what we're doing is we're taking out this overlap. This overlap where population overlaps with violent crime over here, and the overlap between population and number of churches. this overlap. There's actually more overlap here, but I'm more concerned about the one with the correlation. So there's this overlap. So it's overlapping quite a bit, but there is this one thing right here that's intersecting. That's actually the correlation between churches and violent crimes. So we're going to take this out. And we're going to say that we should really look at this, the partial correlation, PR. And so in this case, because we found that there was substantial overlap between our two variables and how they correlate and the population of the city, we're going to take this out. And then we're left with this little area right here. We're left with a smaller area, and that's the partial correlation. And let's just say, theoretically, the partial correlation is 0.20. So by measuring that third variable of population, and then taking it out, this black area here, out of the correlation between those two variables of number of churches and number of violent crimes, we've reduced the correlation from 0.40 to 0.20. So it's a much smaller correlation because there's an overlap with population. So that's conceptually what a partial correlation is doing. It's saying, yeah, these two things might be related, but let's look at a third variable, population in this case, that we think is going to overlap quite a bit with those other two variables and reduce the correlation. And so if we do this and we reduce the correlation quite a bit, then we start thinking, well, then there's probably a more complex picture here. There's probably a lot of other variables going on. Relatedly, if we did the same thing, and let's just say we had, and let's not stick with this variables, let's just say theoretical variables, it doesn't really matter. We have this, and then we do a partial correlation. And if our partial correlation is not that much reduced, let's just say it's 0.35. And so if we had that sort of same thing there, hope I can draw it. Those are the two variables. And let's say the third variable had a very small overlap with these other two. So the variable is the correlation between x and y. That's x, believe it or not. Make it a little bit better. Between x and y is this whole thing right here. This line right here. Hope you can see my cursor. Is this line right here, all of it. And then our third variable, z, comes up, but it only overlaps a little bit. Unlike this one took like half of the space. This one takes up a little bit of the space. So here the partial correlation is still pretty large. There's not much of a reduction from the correlation to the partial correlation because this third variable didn't do much to eat up that relationship. So in this case, then we might say, well, maybe there might be a simpler relationship there. Maybe really there is something about x and y together that's really pushing a lot of the variance in each other. Because once we measured this third variable that we think makes a difference, it didn't make much of a difference. It didn't reduce the correlation much. So a partial correlation can actually answer this type of question. Is the picture much more complex than what we thought, and we need to sort of pump the brakes and say we need to think more about this? Or we looked at something that people said, well, you really need to look at this because it's going to affect everything, and it doesn't really, let's say it doesn't really affect it, then we have some evidence that maybe we should concentrate on this link because it seems to be the big thing. So conceptually, that's what a partial correlation is doing. Again, you do not need to calculate this. There is a way that you can do this on SPSS. There is an SPSS lab. I haven't looked at it yet, so I can't remember if we have a partial correlation there. I'm not sure. But in SPSS, you can run these partial correlations to see if there is a third variable or other variables that reduce the relationship between two things, or whether it doesn't. And so this is a stronger test. So a point of doing the partial correlation is that, sometimes people say, well, you just measure these two things and yeah, there's going to be a correlation there, but that's not a very complex picture. You didn't include this thing. And so if you do this and your correlation gets reduced quite a bit, then you say, okay, you're right. things are complex and things are overlapping with each other, so I need to be quiet a little bit about my two variables. Or conversely, if you say, okay, I strongly believe in these two variables, there's a lot of evidence and good arguments for them being linked, I'm going to take your suggestion about measuring the third thing, I'm going to do it, I'm going to play a fair game. And then if measuring that third variable doesn't reduce my correlation much, the partial correlation is not much smaller than my simple correlation between the two variables, so there's not much of a reduction, then I have a very strong test of the correlation between these two things because I've measured something else and it didn't take away a lot from the relationship. So it's a stronger test of the relationship between two variables if the partial correlation is not going to be much smaller than your simple correlation between the two variables. Okay, again, before we do start the calculations, in some ways it makes some sense. We did the formula a while ago, but let's just get the conceptual stuff out of the way, and then we'll do a bunch of the formulas all together at the end. And so we've been talking about Pearson correlation. And so Pearson correlation is again between two variables that have at least interval level measurement. But there's other correlations that are not linear. So there are correlations we can have that are nominal and ordinal. And one that we're going to actually do in a bit is what's called the Spearmint. So Spearmint is the only thing we're going to do in our class with ordinal data. So why do we want to use ordinal data with correlations? Well, let's look at an example. So let's just say that we look at this. So it looks like when we look at the amount of practice, X, that's the horizontal, and the level of performance, Y, that's the vertical. When we plot this, it's not a line, it's a curve. And so let's say that we're simplistic in our thinking and we can't analyze this, but really we can analyze it if we want to. But let's just say that we don't want to do this. Let's look at the rank order. So if you see here, and this is a very small sample, we look at the X scores, the practice, and the performance, and it looks like this curve. We can actually rank these things. So person B is the lowest on both variables. Person D is second lowest on both. Person A is third lowest on both. C is highest on both. So if we plot the ranks, 1 being lowest, 2 being second place, 3 being second highest, and C being the highest. If we plot the ranks, 4 is the highest, 3 is second, 2 is third, and 1 is the lowest. If we plot the ranks, it starts looking like a perfect correlation. So we can actually sometimes convert our scores to ordinal level data, convert them to ranks, and the relationship becomes clearer. And so let's go through, since we're here, I want to go through our Pearson and our Spearmint. Because in the Pearson, or I'm sorry, in the Spearmint, all we're simply doing is we're taking everybody's scores and just converting it to a rank, with the lowest score being 1. So the rank for B is 1 on both X and Y, because they're down here. The rank for D is 2, because they're second lowest on X, second lowest on Y. So D is 2 and 2. A, 3. They're the third lowest on both variables. And C is 4. They're the highest on both variables. So all we're doing in the Spearmint is we're converting the scores into ranks, and then we're applying the same formula for our Pearson. So actually, let's go through examples of both of these, because it'll be nice to do it side by side. So let's start with the Pearson first. So I'm going to show you something. I'm going to have you copy this because I don't want to post it because it has all the answers on it. So I'm going to show you one example. And again, we're going to start with Pearson. And here's the formula for Pearson. Remember, we have to do the SP over the square root of the sum of squares for x, sum of squares for y. Well, what's SP? We have to take x times y for everybody, add that, add the score for x for everybody, multiply that by the sum of y for everybody, and divide it by n. N is the number of people. So it's pretty simple formulas. So let's do an example. And again, this is Pearson. So go ahead and copy these data. And I can't go any further. Oh, here I can. So here's our first correlation. So we're going to look at narcissism and aggression at ego threat. Aggression at ego threat is when somebody says something different from the person. So it threatens their ego. It threatens their sense that they're superior to other people. So for narcissists, when they are threatened in terms of their ego, they tend to lash out and act aggressively towards other people. And so here's our study. So each person, we've measured their narcissism and we've measured their aggression at ego threat. So person number 1, here's their scores. Sorry about this, I don't know why it's not highlighting it well. Yeah, person number 1, here's their scores. Person 2, here's their scores. If I can get it going right. So person 2, here's their scores. It's not really working well. PDFs are hard to do this sometimes. Person 3, here's their scores on the 2 variables, narcissism, aggression, at ego threat. Person 4, person 5, person 6. So we have 6 people. So each of our 6 people in this study, we've measured them on narcissism and we've measured them on aggression. And we're going to stick with our Pearson first. We'll do Spearmint in a second. So let's do Pearson first. And I'm going to show you how to do this. It's actually very simple. So the first step that I always do is I go ahead and multiply x and y. What are x and y? Well, that's narcissism and aggression. So person 1, 90 times 9. That's 810. So we get some big numbers here. So 810. Person number 2, 80 times 7. That's 560. Person 3, 50 times 3 is 150. Person 4, 20 times 4, 80, etc. So for every person, we're multiplying their score in X, narcissism, times the score in Y, and we're putting it here for every person. The PDF sucks sometimes. So for every person, we have that multiplication score. Then it's really easy. Now I have this column for X and Y for everybody, for 6 people. Now I'm going to add all of these columns. So I'm going to add their scores on narcissism. That's the sum of X. Sum of X. I'm going to add their scores on aggression. That's the sum of Y. I'm going to add their scores on X times Y. That's the sum of X, Y. And then since I'm here, I know I need the sum of squares for X, and I need the sum of squares for Y. So if I go to the online calculator, I put these numbers in, I get the sum of squares for X as this. I go to the online calculator, and I put these data into the sum of squares calculator. I get the sum of squares as this for Y. That's all we need to do for our worksheet. We're ready to roll. We can figure out the correlation now. So remember that the cross product, which is on top of that ratio for the R, the SP is the sum of XY. So remember, XY is over here, minus the sum of X, which is here, times the sum of Y, which is here. Sum of Y is here, if you'll cooperate with me, 34. And N we know is 6. There's 6 scores there, so we just plug it in. It's really easy. The sum of XY, the sum of this column, 2,110. 2,110 comes first. Then we take the sum of X, which is 330, right here, times the sum of Y, 34. 330 times 34, and then we have to divide that by 6. We had 6 people. Now we just solve it. So first thing we need to do is we need to multiply 330 times 34. 330 times 34 is 11,220. Then we have to divide that 11,220 by 6. We get 1870. So now we take the sum of xy, which has been waiting there, 2,110, minus 1,870, and we get 240. 240 is our SP. That's the top part of our correlation formula. Remember, SP goes on top. On the bottom, we're going to multiply the sum of squares x times the sum of squares y and take that square root. What's the sum of squares x, sum of squares y? Well, remember, we found the sum of squares for x. We found the sum of squares for y from our online calculator using those data. So now we just plug everything in. So SP is 240. We just found that out. So SP is 240. So 240 divided by the square root of 3,750, which was the sum of squares for x in our table above, times 23.33, which is the sum of squares for y. So we have 240 again. We're waiting for the bottom to be solved. So 3,750 times 23.33 is, we get large numbers here in correlations, 87,487.5. We take the square root of that number, it's 295.78. Now we can solve. SP 240 divided by 295.78. And here we have a whopping R correlation of 0.81. Since we're here, let's go ahead and square that. So 0.81 times 0.81 is 0.66. So R squared is 0.66. So is that significant? Well, we need a critical value. So remember, we have 6 people. Degrees of freedom in a correlation is n minus 2, because we have 2 variables. So 6 people minus 2 is 4. We go to the table, which is right here. One-tailed, 0.05. So we're right here, and we're looking for 4 degrees of freedom because we had 6 minus 2. Our critical value is 0.729. Sorry about that. It's actually up here. I rounded up to 0.73. So remember that we got 0.81 for our R. Our calculated value, 0.81, is greater than the table value of 0.73, so we reject the HO. So that means that there's a significant relationship, and it's a positive relationship, so we can just simply report this now. There was a significant Y because we rejected the HO. There was a significant positive correlation between narcissism and aggression under ego threat. So that little sentence that says, 1, is it significant or not? 2, if it's significant, what direction, positive or negative? Make sure you say what the variables are. Then we give our stat information. R is the correlation, is 0.81. We rejected the HO, so P is less than 0.05. 0.81 times 0.81 was an R squared of 0.66. Probably we should say it's large. I guess I'll leave it up to you for this one. Typically in this type of a research design where it's correlational, most people understand what R squared is. And they don't need to be told whether it's small, medium, or large because they are able to understand that 0.66 means that 66% of the aggression under ego threat was directly linked to one's level of narcissism. That's it. I hope that you see that and you think, oh my gosh, that's really simple. So keep these numbers. So if you want to keep these numbers for reference for when we do the Spearmint. So since we're fresh on this topic, let's have you do a Pearson correlation. So just using those interval level data. So do it for yourself here, and I have the formulas here if you want them. So go ahead, you solve this, and we have a narcissism theme to this lecture apparently. And so let's say that we have an idea that narcissism is probably negatively related to empathy. Empathy, understanding other people's emotions, having some emotional understanding of what other people are feeling. Narcissists typically don't understand emotions very well. They're very defensive about emotions, and they are definitely not very empathetic. And so, unless they can feign it sometimes because they might ask how you are, how are you doing. They're very good at sort of doing that type of thing. But if your emotions are what we call hot, if you're really feeling some sort of strong emotion, they're quite perplexed by that, and they usually will avoid such a situation. I'm not talking about hot anger. I'm talking about, it could be hot sadness, it could be hot frustration, it could be a hot disappointment. So it's not necessarily being angry, it's just your emotional level is up. They are not good with emotions, they tend to avoid it. So anyway, let's collect some data. So we collected some data. So here we have 7 people. For each person, we have their score on narcissism. We have their score on empathy. So is there a correlation between narcissism and empathy in these data that we collected from our sample? Here's a formula for SP. Here's a formula for R. You need to find SP first and then R. Remember to do the little worksheet. Multiply the narcissism score with empathy. You'll have a column here of X and Y. Then once you have that new column of X and Y, then you can add up the sum of X, add up the sum of Y, add up that new column, the sum of XY. Then the only other thing that you need to do is use the online calculator to find the sum of squares for X, sum of squares for Y. So go ahead and pause this video and solve for this Pearson correlation. And start the video when you are done with your problem. Okay, you should be done now. Let's go through the answer. So remember, the first step is to compute XY for everybody. So take person 1 score, 85, times 4, 340. Person 2, 66 on X, 5 on Y, 66 times 5 is 330. So for every single person, multiply their score on X, narcissism, with their score on Y. Put that XY here in this new column. Add each of these columns. The sum of X is this. Sum of Y, if I can highlight it with this PDF. Sum of Y is this, and sum of XY is that. Take these scores. I hate PDFs sometimes. Take these scores. No, Bing can be quiet on that. So take these scores. Take everybody's score on narcissism, X. And then we can compute the sum of squares. I almost forgot where it was. Sum of squares from our online calculator. Take that same online calculator, put these scores in. We get the sum of squares for Y. Now we're ready to go. We can do the correlation with these numbers now. So SP is the sum of XY, 1,814 from here, minus the sum of X, 374, right here, times sum of Y, sorry about that, 39, divided by 7, the N here. So our sum of xy will weight as we multiply the sum of x times the sum of y equals this, 14,586. Then we have to divide that by n. N is 7. We have 7 people in our sample. So 14,586 divided by 7 is 2,083.7. So our sum of xy, 1,814 minus 2,083.71. Our SP is negative 269.71. You might think, oh my God, I thought we're not supposed to have negatives. Well, this is not a sum of squares. This is just the sum of products. If you have a negative correlation, you're going to get a negative SP because your sum of squares can't be negative, right? Remember, we just said that just now. So your sum of squares x, your sum of squares y, they can't be negative. You can't have negative variance. There's no such thing. So the thing that determines whether something is a positive correlation or a negative correlation is SP. So in this case, this is indicating that we're going to have a negative correlation. Well, why is that? Well, here's somebody high on narcissism, and they're low on empathy. And just kind of looking, there's somebody low on narcissism, and they're high on empathy. So it looks like there's a pattern that, people who are higher on narcissism are lower on empathy, and people who are lower on narcissism look like they're higher on empathy. That's a negative correlation. As narcissism goes up, empathy goes down. As narcissism goes down, empathy goes up. So that's why we have a negative SP there. Now we can plug things in for the R. SP over the square root of sum of squares x, sum of squares y. So our SP that we just figured out is here. That goes on top. That will wait for us to solve the bottom. So here's our sum of squares x times our sum of squares y from our table above. We calculated that with the online calculator. So we multiply those two numbers, we get 91,379.54. Again, we get large numbers with these correlations. We take the square root of that. The square root of that number is 302.29. Now we're ready to solve. SP divided by the product of the bottom. So negative 269.71 was our SP, divided by 302.29. So our correlation is a negative 0.89. And then let's R-square that right away. I usually like to R-square it because it's right there, it's ready to go. So negative 0.89 times negative 0.9 is going to be positive. Our R-square is always going to be positive. Our R-square is a whopping 0.79. We have to find a critical value. We had 7 people in our study, so 7 minus 2, we have 2 variables. 7 minus 2 is 5 degrees of freedom. So we go to our critical table. One tail test 0.05. We have 5 degrees of freedom. So it looks like our critical value is 0.669. I rounded it up to 0.67 because we rounded up for the correlation. We look at the absolute value. Remember that the positive and negative is just simply telling us the direction of the number of the correlation. So the absolute value is 0.89. That's greater than our critical value. So we reject the HO. So we reject our HO. Now we're ready to write up everything. There was a significant Y because we rejected the HO. Negative correlation is negative 0.89. Between what things? Well, between narcissism and empathy. So the simple sentence just says whether it's significant or not and the direction, if it's significant. If it's not significant, don't give the direction. Just say there was no significant correlation between X and Y. So if there's a significant correlation, say what the direction is. Significant, negative correlation between what 2 things? Narcissism and empathy. What are the numbers? Well, R, negative 0.89, We rejected the HO, so P is less than 0.05. And then we have an R-square of 0.79. Again, in correlational presentations, typically we don't include the small, medium, and large because people tend to know what the R-squared means in this type of an approach. And so here, what that means is R-squared of 0.79 is that 79% of the variance in the empathy scores was directly linked to the person's level of narcissism. Okay, I hope you find that to be pretty easy. Let's do the Spearmint. So remember, Spearmint is we're converting our interval level data into ordinal. Because remember with the Spearmint, I'll go back a little bit, is we might have a situation like this where it looks like a curve, and then if we rank order the data, the relationship looks clearer. And basically to rank it, we start within each variable, and we give 1 to the lowest number, 2 to the second lowest, until the highest one would be the number of scores you have. So if you have 10 people, the highest score would be 10. So lowest score is 1, highest score is however many scores you have. And we simply take those ranks and use the Pearson formula. So I'm going to take you through an example. And we're using the same numbers. And so usually what you want to do is you want to keep your old numbers because you've actually already calculated some of this stuff. Well, not for this one, for the linear equations that we'll talk about in a bit. So sorry about that. That's for simple regression. These are new numbers, so we have to recalculate everything. Step number 1, I'm going to use the same scores. So these scores are the same as from the first example. So remember, the scores were 90, 80, 50, 20, 30, 60 on narcissism, 9, 7, 3, 4, 5, 6. These are the same numbers that we had in our first example that I went over for the Pearson. But now we're going to do a Spearmint. So Spearmint means we have to put these in ranks. You take each variable separate. So I'm going to start with narcissism. Remember, 1 goes to the lowest score. What's the lowest score on narcissism? Well, it's 20. So they get a rank of 1. So I'm going to put the ranks over here. Second lowest score is 30. They get a rank of 2. Next lowest is 50. They get a rank of 3. Next lowest is 60. They get a rank of 4. Next lowest, 80. They get a rank of 5. And the highest score, because we had 6 people here, you can see 6 people on the left-hand side there. The highest score was 90. They get a rank of 6. Then you do the same thing for the other variable, aggression. What was the lowest score in aggression? Well, there's a 3 here. They get a 1. Next lowest was 4. They get a 2. Next lowest is 5. They get a 3. Next lowest is 6. They get a 4. Next lowest is 7. They get a 5. The highest aggression score was 9. They get a rank of 6. There's 6 people. So you might be asking, what do you do if there are ties in the ranks? It makes it just more complicated. The rule is just basically, I think you give 1.5 or 6.5 if they're in between. I'm not going to care a lot about that. So I believe every example that we have here that we're doing live, every example in your homework, and anything that you're asked to do on the exam are not going to have ties. That's just minutia. Doesn't necessarily help you learn anything. It's really just a procedural thing. Let's just think about things more simply and conceptually. So what we're going to do now is I'm going to take all of these rank scores. So remember, in the Spearmint, we care about ordinal data. The ordinal data are the ranks. So we're going to ignore these scores. We're going to just use the ranks. We're just going to use the ranks. So that's my data now. So I'm going to take those ranks and I'm going to put them in my data set. Here's my ranks. So X now is the ranks for narcissism. Y now are the ranks for aggression under ego threat. I do the same exact thing. I have an XY. I'm not sure why I didn't put an XY here, but this is XY. So again, this is with the rank data. So I multiply X times Y. 6 times 6 is 36 for person 1. 5 times 5 is 25. Person 3, 3 times 1 is 3, etc. So I'm just doing the same thing. I'm taking the ranks as my data. I'm multiplying X times Y to get XY here in this column. Once I've done that, then I can add things. So I add X together for the ranks. I add Y together. Notice for the sum of X and the sum of Y, they're going to be the same. Why are they the same? Well, you have 6 people, so you're going to rank 1 through 6. You're going to have 1, 2, 3, 4, 5, 6. Same thing for Y. You're going to rank 1 through 6. You're going to have 1, 2, 3, 4, 5, 6. You're going to have the same exact numbers. You have the same exact numbers. You're going to have the same exact sum. And guess what? Same exact numbers. You're also going to have the same exact sum of squares for X as you do for Y. So now you might be thinking, oh, this is actually looking a little bit more simpler now. So you just plug those numbers in. SP, sum of XY, minus sum of X times sum of Y over N. N is the number of people here. We have 6. SP, sum of XY was 88, right here. 88. Sum of X is 21, and the sum of Y is 21. They're going to be the same. And you're going to divide that product by 6. So you take, and I have it solved here, but I'll show you in case you want to see it. So we have 21 times 21, that's the sum of X times the sum of Y. That's 441. We divide it by N. There's 6 people in our sample. So 73.5 is this ratio right here. So we take the sum of XY, 88, minus 73.5. We have an SP of 14.5. So now we know we take that SP and we divide it by the square root of sum of squares X, sum of squares Y. We know the sum of squares X and Y are the same, 17.5. So now we have this. Here's our SP. This is our calculation of the Spearmint R. SP and then square root of sum of squares X times sum of squares Y. Sum of squares X times sum of squares Y is this. That's the product. Take the square root of that, we get 17.5. So now we have our SP divided by the bottom part, the square root of sum of squares X, sum of squares Y. We have a correlation of 0.83. If you remember, that's not too far from what we got from the Pearson. So why is that? Probably because we had a pretty good linear relationship anyway, but this is just to show you how to do it with ordinal data with a Spearmint. So our degrees of freedom is actually the same as before. We have 6 people minus 2. We have 4 degrees of freedom. 4 degrees of freedom. We look at this column, one tail test, 0.05, 4 degrees of freedom, 0.729, I rounded up to 0.73. We make the same conclusion. So 0.83 is greater than 0.73 from our table, so we reject the HO. And then we can do the R squared. I guess I just report the R squared down here. I just want to double check that's correct, since I don't have it above. So 0.83 times 0.83, yep, 69. So what we do is we just say we converted the data to ranks in order to do a Spearmint correlation. So we're doing ordinal data with a Spearmint. Then everything's kind of the same format. We rejected HO, so we say there's a significant correlation. Since it's significant, we say the direction is positive. There was a significant positive correlation between what? Between narcissism and aggression under ego threat. R equals 0.83. That's what we calculated above. We rejected the HO, so P is less than 0.05. 0.83 times 0.83 was 0.69. What does that mean? That means 69% of the variance in aggression under ego threat was directly linked to one's level of narcissism. So go ahead and do a Spearmint correlation on your own with the same data that we had before. So this is the same data as what we had for narcissism and empathy before when we did Pearson. Now do a Spearmint. You can pause it if you're ready to go. You can listen for a few more seconds if you're not. If you're not ready to go, just remember your first step is to take each variable and rank the scores within it. So you need to rank people's scores on narcissism, with 1 being the lowest score, and then a rank of 7, because we have 7 people in our sample, being the highest score on narcissism. Then you're going to rank people's scores on empathy, with the lowest score on empathy in the sample as a 1, and the highest score on empathy as a 7. Again, we have 7 people in our study. And then once you have the ranks, you use the ranks as the data. So you're going to have scores of 1 through 7 for narcissism and scores 1 through 7 for empathy. Those are your data. You use the ranks. You're going to follow the same process as the Pearson. You're going to multiply those rank scores for X and Y to get the XY in the third column, or fourth column, I should say, but third column of data on the right. Then you're going to add the scores on the narcissism ranks. So you're going to have that, and it should be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. That's the sum of X, because we're using the rank scores. If you want, you can do the same thing for empathy for Y, but it should be the same sum, because you're going to have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Then add the XYs, that last column, and then get the sum of squares for X. So you're going to put 1, 2, 3, 4, 5, 6, 7 into the sum of squares calculator and find the sum of squares for those numbers. That's your sum of squares X. That also will be your sum of squares for Y, because Y is also 1, 2, 3, 4, 5, 6, 7. Should be the same thing. So now, if you needed that extra help, now pause it and then do the solution. Once you have the solution, then turn the video back on and we'll go over it. So here should be your ranks. So here's the ranks on narcissism. 1 being the lowest score on narcissism, 7 being the highest score in our sample. And then the lowest score on empathy is a rank of 1. Highest score on empathy, highest score on empathy is a 7. Then you take those ranks and you put them down as your data. So here's the ranks on narcissism, ranks on empathy. So this is now X, this is now Y. For each person, multiply X times Y. 7 times 3 is 21. Person 3, 6 times 2 is 12. So here's our XYs now. So our sum of X, 1 plus 2 plus 3 plus 4, 5, 6, 7 is 28. Our sum of Y is 28. And then our sum, I'm sorry. Actually, you should be glad it's a burp. I feel like I need to fart also. Then we have our sum of XY. It's 96. I don't have the sum of squares here because I think I have it down here. So our sum of squares should be 28. Oh, just wait. I hope that's not wrong. I might have a mistake in here, which I'm going to rectify. Give me a second. So we have 1 through 7, correct? Yep. And then we calculate it, And our sum of squares is probably not 28. It actually is 28. What are the chances of that? Let me actually, now I'm getting paranoid about adding them together. Plus 2, plus 3, plus 4, plus 5, plus, whoops, get back there, plus 5, plus 6, plus 7, 28. Anyway, I'm not going to think too much about that. There might be a relationship there, but I am pretty tired, and you're probably pretty tired, so let's just say it's very easy to add those numbers together, so we have 28. So let's go ahead and plug. So SP is sum of xy minus sum of x times minus sum of y over n. So our sum of xy is 96. Our sum of x was 28, and that's also going to be the same sum for y. So 28, and I don't have this throughout the whole steps, I'll do it for you right here. 28 times 28 equals 700. Divide that by 7. That's 100. Ooh, let me do that again. I do not like this when things don't work out. Ah, I must have pressed something wrong. 28 times 28 is 784. Since I did this before, I trust that more. Divided by 7, that's 112. So now we have 96, which was the sum of xy, minus 112. It's negative 16. Why is it negative? Well, it's negative because we have a negative relationship between narcissism and empathy. We saw that already with the Pearson. It actually looks like it's true here. Look at the highest narcissism person. They got a rank of 3 on empathy. Our second highest on narcissism got a 2 on empathy. Our lowest person on narcissism had the highest score on empathy. Our second lowest score on narcissism got the second highest score on empathy. So it looks like it's negative. So we have a negative SP because we have a negative correlation. It's smaller here, right? The numbers look like really reasonable now because we're just using ranks rather than the scores. So now we can do our R. R is SP divided by the square root of sum of squares x times sum of squares y. So our SP was negative 16. We calculated it just now. Then we take the square root of 28 times 28. And guess what? If you don't believe me, I'll do it for you. It's pretty easy, right? 28 times 28 equals this. And then we take the square root, we're back to 28. Pretty simple stuff, right? So negative 16 divided by 28. So our Spearmint correlation here, which it went down quite a bit. So there's something to this in terms of the shape of the actual data. It's negative 0.57 is the Spearmint correlation. Our critical value is the same as before. We had a degrees of freedom 5. Why 5? We have 7 people minus 2. We have 2 variables. So we go here, one tail test, 0.05. We go to 5 degrees of freedom right here. 0.669 is our critical value. We can round it up to 0.67. And look at this. Using Spearmint, we actually failed to reject the HO. 0.57, which is what we calculated, is less than the value in a table, so we failed to reject it. So we tell people, our first sentence when we do a Spearmint is that we converted the scores to ranks to do a Spearmint correlation. So here, we have our first example of a non-significant correlation. So the correlation was not significant. Well, what was that? What was the correlation between that wasn't significant? Well, it's between narcissism and empathy. We give our correlation that we calculated negative 0.57, and that's actually a pretty high correlation, but we have a small sample size, so it's not significant. We failed to reject the HO. And 0.57 times 0.57 is 0.33. That's the R squared. When we do correlations, we usually don't do the small, medium, large thing because we know, we look at that, we can say that 33% of the variance in empathy scores was directly related to a person's level of narcissism. So that's how you do a Spearmint. So although this is probably taking you a little bit of time, you're probably thinking that's not really bad compared to doing the ANOVAs. It's pretty straightforward stuff. Okay, so let's continue. There's also this thing called point biserial correlation. We are not going to hand calculate that. But basically, a point biserial, and let's talk about this conceptually. You don't need to know all this other stuff. The only thing that you need to know is point biserial is when you have two variables. One variable is at least interval level measurement, or approximates it. Interval approximates, could be ratio too. But the other variable is dichotomous. Dichotomous meaning that there's only two values to it. Could be 0, 1. Let's say that for some horrendous reason, I don't think you should do this, but you could take a predictor variable and you could convert it to a dichotomous variable. Let's say narcissism. So I have people's scores of narcissism. I measured it as an interval level variable. I could convert that into a dichotomous variable by taking categories and just take a median, find out where half my samples above, half my samples below, do what they call a median split. If you're above the median, I'm going to say you're a 1, you're high in narcissism. If you're below the median, you're 0, you're low on narcissism. I don't recommend doing that, but that's an example of dichotomous, narcissist versus non-narcissist, with using a median split. You could also do a point biserial on independent variable. So let's say that I have two levels of an independent variable. I have red, color red, and I have the color green. So if you saw the color red, I'm going to give you a 1 on the color variable. If you saw the color green, I'm going to give you a 0 on the color variable. So it's dichotomous. So this correlation, so I can take the correlation between color, red versus green, that biserial part of the correlation, and correlate it with your attraction scores, which are approximating interval level measurement. So that would be the point biserial correlation, would be that correlation. Guess what? It's equal to the t. So actually the r square is equal to the t. Those t's are usually above this. So point biserial is just like a t conceptually because you're comparing two groups. You're comparing narcissist, non-narcissist on, let's say, aggression. Or you're comparing people who saw red versus people who saw green. That's the biserial variable, dichotomous variable. And do they differ on attraction? So conceptually, this is very much just like the t. So probably t is easier to deal with. So you probably should do a t, but that's what a point biserial correlation is. You don't need to calculate it. Just remember roughly conceptually what it is. So we just said this. So it's just like an independent t-test, conceptually. What if you have two dichotomous variables? So I wouldn't recommend this, but let's say that you have red and green again. And you say, well, maybe in reality you have some high scores on attraction and low scores on attraction. So I take the median of the attraction scores. If you're above the median, you have high attraction. If you're below the median, you're low attraction. So 1, high attraction, 0, low attraction. So now I have red and green, red 1, green 0, that's one variable. Then I have high attraction 1, low attraction 0. If you have that type of data, you can do what's called a phi coefficient. So that's between two dichotomous variables. Again, you do not need to be able to calculate this. Just conceptually remember what this thing is, roughly. Okay, let's get to the last part of this lecture. The last part of this lecture is linear equations and regression. So remember the title of this lecture was Correlation and Simple Regression. Simple regression is simply taking one variable and predicting it from another variable. So remember when we did the plot of the line in correlation? I'm not going to go way back there. It's way many slides back. So remember there's a line we can plot for the correlation. And using that line, I could probably just draw you one, I guess. That would be probably simpler. That way I don't have to go back and have to come back again and find the right slides. So, oops, sorry about that. I need to actually sketch something. And so remember in the correlation, again, I'm using this little mouse pad on my laptop, so it's hard to draw. But we're correlating X and Y, and then we have dots. These are people's scores on X and Y's. The dots are all over the place. That's a dot, by the way. That's a dot too. And what we end up with is a line, the best fit. And so let's say this is a correlation of like 0.71 or something like that. So we can draw a line. It could be the case that there's none of the actual data are on the line, but what the line does, it minimizes the errors. It minimizes the distances between the line and the real data. So anyway, we have this line now. And so what I'm going to do is I'm actually going to erase a little bit of this. That doesn't really, I'm going to erase that so we don't have any other lines. And so when we say we can make predictions from a correlation, if I know your score on X, I can go up here and I can predict what your score on Y will be because we have that line. If your score on X is this, I'm going to predict your score on Y is this. If your X is here, I'm going to predict your Y is here. So we use that line as prediction, and we know that there's going to be errors because obviously there's things here that are off the line, but we use the line to predict. This line can be expressed as a linear equation. A linear equation. So simple regression is expressing as a linear equation, like you've studied since probably middle school at least, the correlation between X and Y, except you're going to express it as a linear equation. It's going to be the same thing. It means the same thing. It's just going to describe this line, not as R equals 0.71, but it's going to express the line as the slope, Y-intercept, all of that type of stuff that you're used to, which we're going to go over in a second. So that's what a simple regression is you're taking X and you're seeing if you can predict it. I'm sorry, taking Y, you can predict it based on X. So if you know the score on X, you go up from X on that score, you find the line, you go over to the Y-axis, the vertical axis. That's your predicted score on Y based on X, based on the slope of the line. So we just talked about that. I don't know if I had to draw that before, but I wanted to draw it. So here there's a correlation. It's probably about like 0.6 something between high school GPA and university GPA. And we can predict if you have a high school GPA of 3, you're gonna go up here. And your university GPA is going to be hopefully not 3, maybe like 2.8. It's not a perfect correlation. And so simple regression is just one variable, university GPA, being predicted by one other variable, high school GPA. Why do I say predict university versus high school GPA? Because this is on the vertical axis. So usually that dependent variable, the thing that you are trying to predict, is over here on the vertical, and the predictor variable is on the horizontal. So remember from your olden days, when you studied lines and equations for lines, it looked like an equation like this. So Y in this case, remember, was university GPA. University GPA can be predicted by knowing the slope of that line times X. So X times the slope of the line plus the Y-intercept. So when we have a bunch of data for X and Y, we can figure out what the slope is and what the Y-intercept is and put these details into this equation. And we're actually going to be using the numbers and the variables that we had for the Pearson correlation to do our linear equation stuff. So whenever you're doing this, it's always helpful to keep your stuff there from the Pearson correlation, because that's going to be used directly to do the linear equation calculations. So we talked about this already with correlations, but with regression, just like correlation, we're going to have a line of best fit. It's called line of best fit. Why is it called line of best fit? Because it minimizes the prediction errors. So what's the prediction errors? Well, here's the prediction error right here. It's the difference between a dot and, I actually want to draw on this, a dot and the line. Because remember, the line is just coming from the best fitting line. Just based on the data, what does the correlation look like? What's the line look like? But we know that there's going to be quite a few dots that are off that line. And so when we say it's a line of best fit and we're minimizing errors, what we're doing is we're minimizing the total distance between the dots and the line. So here, it sounds like a dog's attacking somebody outside. Maybe it's just a hungry dog eating this dinner. Hopefully it's not a person. So there's a dot here, and then the line's here. So this is an error. So every single one of these dots to the line is error, what we call error, because the line says if you're at X here, your Y should be here, but it's not in reality. So there's people that are off the line. So these are all errors. I probably won't draw all of these. So all these distances from the dots to the line are errors. And so what the line, how the line is the best fitting line is that you take all of the errors. So you add up all the errors. It's not hard to figure this out mathematically. It's just simply taking, you're here, your Y is here, but the line says your Y should be here. You just subtract this prediction from the reality. And that equals your error. Your prediction from the reality, that's the error, that's the distance. So you're going to add all these together. For every single score, you're going to add all of these together. That line is the lowest total error. So mathematically what's going on is the equations figure out how to minimize, have the lowest amount of error in total for the whole sample, and that's what the line is. This line is literally the best line in terms of having the lowest total amount of errors for everybody in our sample. That's what that means. That's how you do the correlation too. It's the same thing. And the bottom part here is just saying you're squaring it. Why are we squaring the error prediction? Because we have some, we have some things that are below the prediction. It might be a positive error because the prediction is greater than the reality, and it might be a negative error. So we don't want these things added up, because if we add all the positives and all the negatives, we're going to come up with zero. So we don't want zero error. There's not zero error here. So just like with our sum of squares, we don't want to add the difference from everybody's score to the mean, because it comes out as zero. Same thing as this. If you take people's real scores and subtract it from the predicted score on Y, if you add those together, it's going to be zero. So you have to square them. So that's what this was saying. And then this method is actually called the least squared error. What's least squared error? It just means that you are minimizing the total error for everybody in the sample. Just what we said before when I was drawing it. Okay, that's the conceptual. Let's get to the the brass tacks, as my grandparents would probably say. So we have this equation line. We've changed it a little bit here. So instead of saying y, we're saying predicted y. So that's why that little, we call it hat, y hat. It has a little hat here. It means the predicted y. Well, the predicted y, we can predict y if we know the slope of the line. We know the value of x for that person. And we know the y-intercept. So if we know these things, we can come up with y. We just plug in the numbers. We plug in the slope, we plug in the person's value on x, we plug in the y-intercept, and then bam, we can predict that person's score on y. Okay, it's really simple actually. So b is the slope. You could calculate the slope with this. You can take the correlation and multiply that by the standard deviation of y, standard deviation of x, that ratio. You can do that if you want. If you do it that way, good luck, because there's extra work. Or we can simply figure out the slope of the line by finding the SP, which we've already done for the Pearson correlation, and divide that by the sum of squares of x, which we already did for the Pearson correlation. So I vote for this one. And then to find the y-intercept, which is a in this formula, we simply take the mean of y, we subtract the product of the slope times the mean of x. So these are very simple formulas. So let's do some examples. And we're going to use the same exact data as we used for the Pearson correlation. So let's do our first one. I'll do an example, and then I'll have you do one, and we'll go through the solution together. This is the same example, same data as what we did in our Pearson. So I don't know if I have the table here. I don't need a table. I'm going to show you it. So remember our first example? We did all of this for the Pearson. We did all of this stuff. We found that the sum of squares for x was this, sum of squares for y was this. And here you have to make sure that you keep track of your x's and y's. So sum of squares for x, which was narcissism, here. Sum of squares for y was here. So just remember this. Remember our SP we calculated from the Pearson was 240. So we're actually ready to roll. The only thing that we need to do the linear equation, the only thing that we need is we need the mean of x and the mean of y. We didn't do that. We didn't need that for the correlation. We need it for the linear equation, and that's real easy because we already did the sum of x and the sum of y above. So all we simply do is take the sum of x, divide it by 6. The mean of narcissism, x, is 55. So the sum of y was 34. 34 divided by 6 people. The mean of y is this. That's the only thing that we need that's new. Now we're ready to roll. So this is just showing, remember, that the SP was 240. We calculated that before for the Pearson. So let's get going on the regression. Let's take the easy way out. So the slope will be SP, which is 240. We calculated that already, divided by the sum of squares of x. If you go back to our Pearson correlation calculation of these data, we had the sum of squares x, which was 3,750. So this is very simple. The slope is SP divided by sum of squares of x. 240 divided by 3,750. So 0.06 is our slope. What does that mean? It means for each point change on narcissism, it's related to a change in aggression of 0.06. So let's say we compare two people. One person has a score of 80 on narcissism, the other one scores on 90. So this line would say that that person who has 10 more points on narcissism should have an aggression score that is 0.6 points higher. So let's say that the person who has 80 on narcissism has an aggression score of 10. Let's make it easy. Then we have somebody who gets a score of 90 on narcissism. So they're 10 points higher. Well, that slope would predict that as you move up 10 points from 80 to 90 on narcissism, your regression should go from 10 to 10.6. So that's what the slope is. Okay, now we're ready to get the Y-intercept. The Y-intercept is the mean of Y minus the slope times the mean of X. Remember, the mean of Y and the mean of X is up here. We just calculated that stuff. We knew the sum of X divided by 6 people. Sum of Y divided by 6 people, get the mean of Y. So we have it right there. We just plug things in. And we just got the slope. There's our B, 0.06. So mean of Y was 5.67 minus the slope, 0.06, times the mean of X was 55. So if we take 0.06 times 55, we get 3.3. So we take 5.67 minus 3.3. Our Y-intercept is 2.37. And voila, we can plug in the numbers. So now Y, so our predicted value of the regression score is the slope, 0.06, times somebody's score on aggression, which is, on narcissism, which is X, plus the Y-intercept of 0.237. So if you know somebody's score on X, you can plug it in there. You could solve for this formula to predict their score on Y. So if you know somebody's score on narcissism, you use this formula to predict their score on aggression. This is expressed as a linear equation. Okay, now do it yourself. So go back and use your Pearson correlation stuff that you did for these data. So this is the narcissism empathy. These data are the same as the Pearson. You can go get your SP and your sum of X's and sum of Y's and solve for this. So pause, and I will go over this in a second. Your minutes. Okay, you should be done now if you are watching this. This is the old table. I actually brought the old table down. So we know that this is all the stuff from the Pearson correlation. We knew that the SP, when we calculated it, was negative 269.71. And all we need to do is we need to start going on it. And we have the sum of squares X is right there. Sum of squares X is 3,200, etc. So we simply plug things in. So the slope is the SP that we figured out before, and the sum of squares X that we figured out before. So our slope is negative. This is a negative slope because we had a negative correlation. So remember our other example that we just did, we had a positive correlation, we had a positive slope. Here we have had a negative correlation for the Pearson, and it's a negative slope. And what this is saying is that for every 1 unit change in narcissism leads to a negative 0.08 change in empathy. And by the way, this slope is expressed in the units of measurement. So this is smaller because the empathy scores were quite low, because it was like under 10, right? The empathy scores were, see? We have 3, 4, 5, 6, 8, 9, so they're under 10. So the slope is going to be pretty small there because we're dealing with pretty low scores. So here, if you change the narcissism score from, let's say, 90 to 91, going 1 score higher on narcissism would lead to a reduction of 0.08 in your empathy scores. Sorry about the pause there. There's some screaming going on outside my window. And then once we have the slope, we can then solve for the Y-intercept. So the mean of y and the mean of x. I didn't do that right here, but these should match. I'm going to do it right now. So 374 is the sum of x. We have 7 people, correct? So 5343. Let me check that. 5343 is the mean of x. Yeah. So I don't like using this laptop sometimes. 5343 was the mean of x, and I put it there. See? Mean of x is here, mean of x is here. Mean of y. So the sum of y was 39. 39 divided by 7. 5.57 is the mean of y. $5.57. What was that? I hate when this happens. Oh, that's why I went up too far. 39. That was freaking me out a little bit. 39 divided by 7. 557 should be our mean of y. And yes, indeed, I put 557 as the mean of y. Mean of y. Mean of y, 557, minus the slope, negative 0.08, which is what we just calculated. And multiply that slope by the mean of x, which was 53.43. Negative 0.08 times 53.43 is 427. Don't forget we have a negative times a negative. And so we actually add here. I should say we're subtracting a negative number, so we're actually adding. So 5.57 plus 4.27, our y-intercept is 9.84. You might say, well, why are we adding there instead of subtracting? So think about this, and I'm going to draw this. So think about it this way. I'm going to sketch this in a second. My butt's hurting. That's not part of the lecture. You won't be tested on that. I'm just making a comment. I'm going to make this broad because I want to draw 2 things at once. So remember, when we have a positive correlation, we're starting probably a little bit lower because we have to go higher. And so usually that y-intercept, we're kind of going a little bit down on the y-intercept because we have to go up. And so in this one, we had a negative correlation. You might say, well, why are we adding those numbers there? Oops, that's not where. Why are we adding these numbers? Because we're subtracting it before. We're supposed to subtract, but we're adding it now. Well, this is why. When you have a negative correlation, your y-intercept has to kind of be pushed up a bit, right? Because you're going downwards in a negative correlation. So the y-intercept is going to be pushed up a bit. So that's what's going on. That's why we're adding instead of subtracting. Mathematically, that's what's going on, or conceptually. And so now we can plug in the numbers. We know that our form of our linear equation should be the predicted y is equal to the slope times x plus the y-intercept. So if you want to predict empathy, you can take somebody's score on X narcissism, multiply that by negative 0.08. It's a negative correlation, negative slope, and then add the y-intercept, and then you can predict their empathy by solving this. Plug in X and solve it. You get a prediction for y. So that's all there is. So although we kind of went over many examples there, because we had 3 different ways of sort of looking at the same data, we had the Pearson for the interval correlation. We did the Spearmint where we converted the interval data to rank order, ordinal data. We did a Spearmint correlation, and then we did a linear equation. So it took a little bit of time because we did 2 examples for those 3 different ways of doing it, but I'm guessing each of those different ways are a lot easier than the ANOVA. So just sort of tying these two things together, correlation and simple regression. So as our correlation approaches 1, remember that we had a tighter circle. So if we circled our dots are a tighter circle as our correlation approaches 1. As our correlation gets away from 1, is lower than 1, goes towards 0, our circle around the dots gets wider and bigger because there's more errors. So as we approach 1, a perfect correlation, we have fewer prediction errors. Our predicted Ys are going to be closer to the regression line. So basically what this is saying conceptually is the higher the correlation between two variables, you're going to have much better predictions of Y in your simple regression, your linear equations, because there's fewer errors. If we have a lower correlation, then you're going to have a lot more errors between your predicted Y and your real score on Ys. And you can see that when we were actually looking at this stuff. So I'm actually going to go back a little bit. You can kind of see it like in this one. Looks like the dots are quite a bit off. So these errors, the correlation is going to be smaller than if the dots are closer. Dots are closer, the errors are going to be smaller. Your linear equation is going to make better predictions because you have less errors. If the dots are farther away, then the errors are bigger. And then when you're doing your predictions from the linear equation, your errors are going to be bigger also. So basically, you can test the regression significance. So when you do the regression, it will give you a significance. It's very similar to the ANOVA thing. So all I'll say is it's testing the slope of the regression line, and the HO is that the slope is 0. And basically, it kind of does a two-tail. Doesn't really matter much in this case. And so it's actually doing that test of whether it's different from 0. Because the higher the slope, the farther away from 0, the higher the correlation, the higher the relationship between X and Y are. You don't have to do that. You don't have to do this either. We're going to do an SPSS lab for this class. And so there is going to be a homework and there is going to be an SPSS lab for this material. So hopefully that was not too bad. I know that was a little bit long, but we went over many different examples, doing 3 different ways of looking at the same data. The Pearson correlation, interval to interval correlation. And then we did the Spearmint, where we converted the interval data to ranks. So we did ordinal data. And then we converted our Pearson correlation information into a linear equation. So I am going to stop this. And again, you have homework and SPSS for this material that will be due at the end of this week. Talk to you later.